Hello everyone, this is my teaching experience for the ME555 Spring 2013 semester. I'm going to discuss control-oriented lithium-ion battery modeling. To begin, I want to first explain what control-oriented lithium-ion battery modeling really means. It's a long, wordy title, and it doesn't really make sense to talk about before understanding what it really means. To help you understand it, I'm going to break down the title into three parts. First, what is a lithium-ion battery? Second, what is a model? And third, what do I mean by control-oriented? After I've answered these three previous questions, I'll move to discussing three types of models. First, the equivalent circuit model. Second, the single particle model. And lastly, the pseudo two-dimensional model. I conclude with a brief summary at the end and end with some closing remarks. So starting off, what is a lithium-ion battery? Keeping it simple, it is a type of rechargeable battery that has grown in popularity in the past 2.5 decades. They are found in the cell phones in our pockets, the power tools in our backyard sheds, laptops sitting on our laps, hybrid cars parked in our driveways, and many other places. At the most basic level, batteries consist of three components. The positive electrode, also known as the cathode. This is made up primarily of a lithium metallic oxide, such as lithium iron phosphate, lithium manganese oxide, or lithium cobalt oxide. The separator, where the electrolyte is at. This is normally an organic compound such as ethylene carbonate. Lastly, there is the negative electrode, also known as the anode. Normally this is made of graphite. So the next question I want to answer is, what is a model? It is quite simply a mathematical representation of a physical system. Belongs to a battery model is a mathematical representation of a real battery cell. An example of using a battery model is to study how a battery would react in a cold temperature environment, such as outer space. An important note is that in this presentation, I'm only going to touch upon 3 battery models, but in reality there are many more kinds, each with pros and cons. Choosing which kind you use depends on the problem you're trying to solve. The last question I want to answer is, what do I mean by control-oriented? It sounds quite exotic, but it isn't at all. The answer is that this model can run on a personal computer or microcontroller, such as an Arduino, in real time or even faster. I have 2 examples of this. First, for my own thesis, I want to optimize the charge pattern of a battery, so I need a battery model that can run very quickly on my personal computer. Secondly, for onboard a hybrid car, there might be a battery model running to estimate the lifetime left of the battery cells in the car. There are of course battery models for other purposes that aren't related to controls. An example is a thermal, 3-dimensional model of a battery cell to determine where hotspots are located. This model would be useful for a battery manufacturer when trying to design a cell for a particular application. Now that I've hopefully answered the question, what does control-oriented battery modeling mean, I want to move on and talk about the types of battery models used for control-oriented applications. First, I'm going to start off with the equivalent circuit model. The equivalent circuit model is the simplest model, where the battery is modeled as a voltage source along with some combination of resistors, capacitors, and inductors. In this picture, this is one of the simplest representations of a battery, with one voltage source in series with one resistor attached to some load. Please note that this resistance is considered to be within the battery, so it is known as the internal resistance of a cell. In general, the voltage source, along with the resistors, capacitors, and inductors, are nonlinear and functions of the state of charge. The state of charge is the amount of charge or energy in a battery cell. It is analogous to the gas gauge in a car. An example of this nonlinear voltage source versus SOC curve is shown below. This plot in particular comes from some of the research done in the lab that I belong to at Penn State. To conclude my discussion of equivalent circuit models, I want to talk about the pros and cons. Starting with the pros of this model is, it's easy to make. It's as simple as connecting electrical components in series and in parallel. It is also easy to simulate. The equations follow basic electrical engineering laws. And lastly, it's easy to understand. You don't need to know the chemistry behind the battery, just some basic electrical engineering knowledge, and you can understand this type of battery model. Now moving on to the negatives. You need to run a number of tests to determine nonlinear curves for the electrical components. And to run these tests, you need relatively expensive equipment to do so. More importantly, this model does not help you understand the chemistry going on inside the cell, which is important if you really want to study battery cells. So moving on to a more complex model, we arrive at the single particle model. This model is called a single particle model because it represents the positive electrode and the negative electrode, each as spherical particles where lithium ions diffuse in and out of during charging and recharging. This diffusion process is governed by a fixed second law and the radial direction for each particle. The general equation is shown above. Note there are many more equations needed, but this is the heart of the model. What you might have noticed is that I made no mention of the separator being modeled, because in a single particle model, the diffusion is neglected in the separator. This of course simplifies the model, however it does have consequences. In the plot shown, this is a single particle model undergoing discharge for a half hour. You can clearly see the nonlinear voltage drop as a function of time. The plot itself comes from a class project I did last year. Wrapping up my discussion of single particle models, I'm going to go over the pros and cons. On the plus side, this model does represent the chemistry behind the battery, which is vital for really understanding what is going on under given conditions. However, on the negative side, the equations are much more complex compared to the equivalent circuit model, making it much harder to create the model. Also, from personal experience, it is very hard to get the coefficients needed to simulate the battery model. Without realistic values, the model will not represent the real battery very well. And lastly, because the separator is ignored, this model does a poor job at high current values, which really limits the use of this model for high power applications, such as simulating a hybrid vehicle or something like that. Moving on to the last battery model is the pseudo two-dimensional model. It is similar to the single particle model. Both use spherical parts to represent the positive and negative electrodes. The biggest difference is that the diffusion of lithium ions is modeled in the battery separator. The name pseudo 2D comes from the fact that lithium ions diffuse out of the particles in the radial direction and also linearly diffuse in the separator along the x direction. Finishing up the pseudo 2D model discussion with the pros and cons. On the plus side, it models the positive electrode, negative electrode, and separator, which the two other models failed to do. This provides a better picture of what's going on inside the battery. This model can also accurately model high current values where the single particle model failed. The negative of that is, of course, this is the most complex model out of the three. There are a large number of parameters needed to model this battery well. Also, this model is computationally very difficult to simulate. It requires a lot of math tricks to run quickly on a personal computer. So I'm going to wrap up this presentation with a summary and some final thoughts. To finish up, With the growing use of lithium-ion batteries, there is a growing need to create control-oriented models of these batteries. Three types of control-oriented battery models are the equivalent circuit model, the single particle model, and the pseudo 2D model. These models can span the spectrum from quick and easy to complex and time-consuming to make. Equivalent circuit models are easy to create and use, but don't provide insight to underlying chemical reactions. On the other hand, pseudo two-dimensional models are hard to create, but are accurate and simulates the chemical processes in a battery very well. Thank you for watching. I purposely left out a lot of details of this presentation to keep it short and basic, so if you want to use more, use Google, especially Google Scholar. There are a lot of great resources out there to look up and learn more about lithium-ion batteries. Thank you again for watching. Have a nice day.